should be turned on. We want the mixer to operate for 7 seconds, mixing the liquids that have been pumped into the tank. After 7 seconds, the mixer should automatically shut down, and this discharge valve should open. With the valve open, the liquid will be discharged from the tank and transferred to another location within the factory to be processed. When the level of the liquid in the tank drops to the minimum set level of the lower switch, the switch contacts will close again, thus starting a repeat of the cycle. Okay, so now we need to click on the Somatic Manager desktop icon in order to start writing the program. Somatic Manager is a program which manages sub-programs of Step 7. To start our programming, first, we need to create a new project by clicking on the New icon on the toolbar to open the new project window. In this window, we enter a name for our project in the Name field. We'll call this project Mixer and enter it here. The path to our saved project is shown in the storage location. However, we can use the Browse button to navigate to a different location other than the default. Okay, after creating the project, we click on its name to highlight it. Then, from the Insert menu, we select one of these stations, dependent upon the control system that we intend to use. As we discussed previously, we will be using an S7300 PLC to control our machine. So, we need to select the second option shown here, which is Station 300. After selecting this option, we see that a subgroup named Somatic 300 has been added to our project. Next, we click on this hardware icon, which takes us to the hardware so that we can configure the modules we need for the PLC. Our PLC is an S7300. So we need to select the relevant modules from Somatic 300 subgroup here. First of all, we need a rack into which we will mount the modules. To insert the rack, open the Rack 300 and double-click on the rail to add it to the left window. As you can see, this rack has 11 slots. We need to install a power supply in the first slot to power our PLC modules and turn them on. To do this, we open this PS300 folder and double-click on this 2 ampere power supply to insert it into the first slot of the rack. Note that all the listed PLC modules have an order number or part number, which is displayed in this lower box when each module is clicked on. In real-world projects, the order number of each module that we select should match exactly the module in the enclosure, but as this is a demonstration project for training purposes, we can ignore that requirement for now. Okay, in the second slot of the rack, we always insert the CPU module. To select the desired module, we open this CPU 300 folder, which opens to show us all types of 300 CPUs. We want to select a 316 CPU, so we need to open this CPU 316 folder and click on the relevant part number to insert it into the second slot in the rack. Now, in addition to these two modules, we need an input and an output module, both digital. The input and output modules are both categories in the subgroup SM300. To insert a digital module, we need to open this DI300 folder and double-click on this 24-volt module, which has 16 inputs. However, as you can see, after doing this, we get a message that this module can only be inserted into slots 4 through 11. So we need to leave the third slot empty, select the fourth slot, and then double-click on the module again to insert it into the rack. Now, we can also insert the digital output module by opening the DO300 here. Double-click on this module to insert a 24-volt 16 output module. Okay, the addresses of the digital input module range from byte 0 to byte number 1, which means that the addresses we can use in this module for our program start at I00 for the first input and continue through to I17 for the last input. This gives us 16 digital inputs. Similarly, as you can see, the addresses of our digital output module range from byte number 4 through to byte number 5, so there are 16 addresses that we can use for this module, starting at Q40, continuing through to Q57. Okay, so now the configuration is complete, and we can download it to the PLC. We will use a simulator to test the program, so we need to click on this Simulator On-Off icon in the somatic environment in order to run the simulator program. Now, we go to the Insert menu and select Input Variable so that we can insert an input variable. Similarly, we can select Output Variable, but as the address of our output module starts from byte number 4, we need to change this 0 to a 4. Before downloading the configuration, first click on the Save and Compile icon to save it. Then, we click on this Download icon. This brings up a window where we need to select the CPU to which we want to download the configuration, and then click OK. In the next window, click on View, and then select the appropriate MPI address. And after clicking OK, the configuration will download to the CPU. Now, having completed the configuration, we can check the project tree and see that a subgroup with the same name as the CPU has been added there. Now, we can write our program in a block named OB1. We can find the OB1 by opening the S7 program folder and looking in the block folder. Okay, now we open the OB1 by double-clicking on it. As it's the first time we've opened it, this Properties window opens. We simply OK the window to get into the programming environment. So far, we've learned how to make some basic settings and organize the environment so that we can start programming. In the next lesson, we'll learn how to write a program using simple and practical instructions that will control our machine. So, did you like this video? We hope you did. And if you did, subscribe and share it with your friends. Hello again. In this lesson, we will learn how to write a PLC program for the machine illustrated here by using an S7300 PLC and Step 7 software. As you can see, we have two pumps which are being used to transfer two separate liquids into this tank. Inside the tank, there are two level switches installed in the lower and upper parts of the tank respectively. The switches are digital, which means that they can only ever be in one of two states, true or false.
In this video, we're going to introduce you to a typical PLC and its associated hardware. First of all, let's start with the term PLC and talk about what it means.
If you manage a team, you have to try Monday.com. Monday.com is a platform to track all our projects: marketing, product development, HR, creative productions. I love Monday.com because it's totally customizable, and that's something I couldn't find in.
True or false? Before we start to write the program, we first need to select a name that is representative of the facility shown here. Within this machine, we have these two level switches and this stop switch. These are the machine's inputs. The outputs are these two pumps, the mixer, and this valve. If the low level, high level, and stop switches are connected respectively to the first, second, and third inputs of the PLC input module, their addresses in sequence will be I00, I01, and I02. Similarly, if pumps 1 and 2, the mixer, and the valve are connected respectively to outputs 1 to 4 of the PLC's output module, their addresses will be Q40, Q41, Q42, and Q43 sequentially. Okay, now that we know all the addresses of the inputs and outputs, we can go to the option menu and open the symbol table to give each address a representative name. We enter the name L level for the low level switch and leave the type as Boolean because the switch is digital. We continue naming the addresses with representative names until all addresses have a name. Then we save the table and navigate back to the OB1. Okay, so as we did before, we want this switch here and both pumps to be energized when the level of the liquid in the tank drops to the minimum. We do this by inserting an SR flip-flop from the bit logic folder here. The functions of the flip-flop are quite basic. It has 2 inputs and 1 output. When the set input is energized, the Q output is true, and when the reset input is energized, the Q output is false. So now, we're going to add 2 coils. One will be assigned the address of pump number 1, and the other will be assigned the address of pump number 2. In order to turn on the 2 pumps when the low-level switch is energized, we place an open contact here and assign it to the address of the low-level switch. As we know already, the switch has an open contact inside it, and when the level of the liquid in the tank drops to the minimum, a 24-volt signal is sent to the I00 input, causing this contact to be closed, and the set input to be energized, resulting in the 2 pumps being turned on. Now that our pumps are running, at what point should they be shut down? Well, as we said before, the pumps should run until the level of the liquid in the tank rises to its maximum when the high-level switch is energized. So, let's insert another open contact here and assign it to the address of the high-level switch. So now, when the switch is energized, both pumps will be shut down. We also add the address of a memory bit here for the flip-flop. Okay, so after the tank has been filled and the pumps shut down, we want this mixer to start up automatically to mix the liquid in the tank for 7 seconds. So first, we need to add a new network here, then insert an extended pulse timer here, giving it an address of TO. Now, we add an open contact here for the set input, assigning it the address of the high-level switch. And then we add a coil here for the output, giving it the address of the mixer. Now we need to set the duration of time for the mixer to run in the time valve input, using S5 time formatting. In our case, we want to enter 7 seconds, so first we enter S5T, then the pound sign, and then 7S, which represents 7 seconds. We also need to add an open contact and assign it to the address of the valve for the reset input. Now with these settings, when the high-level switch is energized, the mixer will be turned on and run for 7 seconds. So because the reset input has an open contact with the address of the valve, the mixer can never be energized while the discharge valve is open and liquid is being discharged from the tank. Now, what should happen after the mixer is turned off? That's right, the discharge valve should open to discharge the liquid from the tank to be used elsewhere in the factory. So now, we need to insert a new network and insert another SR flip-flop here. Now, which one of the outputs do we need to turn on with this flip-flop? Yes, it's the valve that we need to activate with this instruction. So we place a coil in the flip-flop output, assigning it the address of the valve. Now, when exactly should this valve be energized? Or in other words, when should the valve open? Right again. As we said earlier, the valve should open after the tank has been filled and the mixer is finished mixing the liquids. So we need to insert an open contact for the high-level switch here, and following that, we insert a closed contact for the mixer. With these settings, when the tank is full and the mixer is off, the valve will open. So how long will the valve stay open? Well, it will remain open until the level of the liquid drops to the minimum set level, which means the tank is fully discharged at this point. So which one of these facilities will be energized when the level reaches the minimum? Right, the low-level switch. So we should insert an open contact into the reset input so that when the switch is energized, the valve will be closed. We also assign an address of M01 to the flip-flop memory. Okay, our program is almost complete, but we also have a stop switch here. Stop switches normally remain closed. This means that the contact within the switch usually remains closed, allowing the signal to pass through them. When the switch is pushed, the contact is opened and the signal is disconnected. The stop switch here is normally closed too, so we can add a closed contact on the reset input of this flip-flop. And we can also copy and paste it for the other networks. With these settings, when the stop switch is pressed, all outputs will be turned off. So that completes the programming. Now, we can save our program and move on to test it. Here, because we are using PCS7 instead of Step 7, this download icon is disabled. So we need to go to the Somatic Manager and click on this icon in the toolbar to open the online window. In the window, open the Block folder and drag the OB1 from the offline window to the online window like this. The offline window contains our computer's data, and the online window contains the PLC's data. This HMI station has been added to the project tree because we're going to use WinCC Flexible to test the program in addition to the PLC simulator. but it's not imperative to use this station. You can test the program using the PLC simulator alone. Okay, now we're going to put the CPU into run mode, and then put the program into online mode. We know that the stop switch is normally closed, so we need to close it manually in the simulator before we can test the program. So to start, we first energize the low-level switch, and as expected, pump numbers 1 and 2 are both turned on. Note that in the simulator, the relevant outputs of Q40 and Q41 are now true, and illustrated in this graphic, you can see both pumps are turned on and are pumping liquid into the tank. When the liquid rises past the level of the low-level switch and it stops being energized, the pumps will continue operating because the tank is not yet full. When the level of the liquid rises to the maximum, the high-level switch is energized, which turns off the pumps and starts the timer. Here, you can see that the mixer is going to be turned on for 7 seconds, and after it's been shut down, the discharge valve will be opened automatically. This process continues until the level of the liquid drops to the minimum again. At this point, the low-level switch will be energized again, the valve will be closed, and the pumps will be turned on, thus repeating the cycle. At any point during the machine's operation, if we press the stop button, all the outputs are turned off, as you see here. Okay, so in this lesson, we learned how to write a program to control this machine automatically using an S7300 PLC and Step 7 software. Thank you very much for watching this video. Make sure you subscribe to Parsec if you haven't already, because we've got some more awesome videos coming your way very soon.
There are 5 languages that are all a part of the IEC, or International Electrotechnical Commission, Section 61131-3 standard. This IEC standard allows some ground rules that standardize PLCs in their languages. Let's take a deeper look into all these PLC programming languages. Before we get started on today's video, if you love our videos, be sure to click the like button below. Then make sure to click subscribe and the little bell to receive notifications of new RealPars videos. This way, you never miss another one. The 5 PLC programming languages are ladder diagram, or LD, sequential function charts, or SFC, function block diagram, or FBD, structured text, or ST, and instruction list, or IL. Let's show you a little bit about each of these. I will start with ladder diagram, which is a graphical type of PLC programming language. Ladder diagram was originally modeled from relay logic, which used physical devices, such as switches and mechanical relays, to control processes. Ladder diagram utilizes internal logic to replace all except the physical devices that need an electrical signal to activate them. Ladder diagram is built in the form of horizontal rungs with 2 vertical rails that represent the electrical connection on relay logic schematics. You can program all the necessary input conditions to affect the output conditions, whether logical or physical. The main advantages of the ladder diagram language are that the rungs allow it to be organized and easy to follow. It also lets you document comments that are readily visible, and it supports online editing very successfully. The main disadvantage is that there are some instructions that are not available, which might make it more difficult for programming, such as motion or batching. The next PLC programming language that I will talk to you about is the sequential function charts, which uses a graphical type of programming. If you have any experience with flowcharts, then this PLC programming language will feel familiar to you. In sequential function charts, you use steps and transitions to achieve your end results. Steps act as a major function in your program. These steps house the actions that occur when you program them to happen. This decision can be based on timing, a certain phase of the process, or a physical state of the equipment. Transitions are the instructions that you use to move from one step to another step by setting conditions of true or false. Unlike traditional flowcharts, the sequential function charts can have multiple paths. You can use branches to initiate multiple steps at one time. A couple of the advantages of sequential function charts are: processes can be broken into major steps that can make it faster and easier troubleshooting. You have direct access in the logic to see where a piece of equipment faulted. It can be faster to design and write the logic due to the ability to use repeated executions of individual pieces of logic. Even when you consider the advantages of the sequential function charts, this PLC programming language does not always fit every application. Now, we are on to our third PLC programming language, the function block diagram, which is also a graphical type of language. The function block diagram describes a function, inputs and outputs that are connected in blocks by connection.